Good day! Welcome to Unit 3, the atom. Everything's made of atoms, and in this unit, we're going to look into how they work and what these atoms are. Okay, first part, models of the atom. What are the atoms? So with models of the atom, we actually have more than one. I'm skipping quite a few. These were created as we started to gain a better and better understanding of the atom. You'll notice I have dates for when these things went live. Dates are plus or minus a few years, just depending on how you want to count them. Unlike, however, most research, where as we discover better and better stuff, we discard the old atoms, we actually keep the older models. We know they're not quite right. We know that they're definitely oversimplifications, but they do have use as a simpler way of understanding things. And the simplest model of the atom comes from John Dalton. There's actually a variant that the Greeks had back in, 600 BC or whatever. But really, the the Greek variant is just kind of nuts because they had bread atoms and they were guessing. But the modern concept of the atom really begins with John Dalton and the billiard ball model. So basically, the idea is you've got small particles. All matter is made up of these small particles, and they're called atoms. You cannot divide, create, destroy, or change atoms. You can only rearrange them. Now, it turns out we can do that, but it requires a nuclear reactor, a nuclear bomb, or a particle accelerator. So essentially, we can't. At least I can't. I don't have access to any of those things. Very few people do. Atoms come in different types, but individual atoms of a particular type are identical. Now, we also know that there's an asterisk on that one. There are some minor variations between atoms, what we call isotopes. We'll talk about that a little bit later. Long story short, though, they're basically identical. They do the same stuff. If you have an atom of carbon, you have an atom of carbon. They're interchangeable. Atoms of different types will have different properties. Some of them don't have that different of a property. Some of them are pretty close, but they are different. Others are, they're definitely totally different. And when we have a chemical reaction, when we have a change that changes the material, we are not changing the atoms. We are rearranging them. If you have 27 carbon atoms, you are stuck with 27 carbon atoms. You can rearrange them all you want, but you've got 27 carbon atoms. Unless, of course, you got like a nuclear reactor or something, but we'll assume you don't. Next up, 1913 is the Bohr model. Yeah, I've skipped a couple. Note the date change. The question is, okay, so we've got these hard billiard balls. Well, what makes up the billiard balls? Niels Bohr is actually a astronomer. He's studying the sun, and we're discovering particles. Now, I'm somewhat misleading here, because the image shows neutrons. Neutrons were not discovered until the 1930s. So the original Bohr model only had protons, but the core model doesn't really change much with neutrons. The neutrons, turns out, are there to help hold the nucleus together, and it also turns out the Bohr model only really works for hydrogen, and most hydrogen atoms don't have a neutron. But anyway, so we've got this one. The idea is that you've got your hard billiard ball, but really what you're seeing with that hard billiard ball is the outer layer of electrons, the electron clouds. So we knew that there were protons, which are these heavy, positively charged particles. Unfortunately, we had already defined positive and negative for charge before we discovered them. Had we had it switched, it would make life so much easier, but we didn't. Oh well. So you've got protons. There's these heavy, positively charged particles. We knew about electrons, these very lightweight, negatively charged particles. We're talking less than 1% the mass of a proton, absolutely tiny little critters. So the Bohr model says you've got the protons in the middle of the atom in what's known as the nucleus. And it's this absolutely tiny. That is not the scale at all. You could not see the proton if that was a scale. We're talking like pixel size. So the idea is you get this absolutely tiny nucleus in the middle of the atom that has all of the mass, and then, or virtually all of the mass, and then the electrons are buzzing around in layers called shells. And the original thought was like orbits, but orbits would decay. These aren't orbits. They are fixed shells, a certain distance apart. Now, of course, Bohr didn't really explain why. We'll get to that here in a little bit. But there's these fixed shells. And it turns out you get some interesting effects with light. As light interacts with an atom, it can absorb the energy from the light, and it will go up, and then the electrons will hop back down into a different shell and give off some light, and that's where he got the shells from, because you don't just get a continuous spread. That's good, but it turns out when you're looking at the spectrum, you're looking at the light coming out of these atoms, this idea of having these shells that the electrons are hopping between works beautifully for hydrogen, and almost works beautifully for nothing else. Or I should say everything else, but not quite. It does not work for the other one, so we had to make things a little bit more advanced. A little bit more advanced was the Schrödinger model. Same basic idea as the Bohr model. You got protons and neutrons in the middle. By the time Schrödinger, well, still no neutrons at this point, but they're coming. Anyways, protons and neutrons in the middle, electrons buzzing around, and that they've got fixed locations. They can't be any old spot. There's these fixed regions of space around the nucleus where the electrons can be. Same as the Bohr model, but the Schrödinger model said, yeah, there are these fixed regions, but they're not all the same shape. And so it's a little bit more complicated story. So in this case, I've got the first, 6 of those things? 5 of those things. And you got your core, what we call the s orbitals, which are spherical in shape, so just like Bohr predicted. But then you've got not just your s orbitals, you got your 1s and your 2s, which is farther out from the nucleus. It takes a little bit more energy for the electrons to buzz there, so they prefer to be in the 1s orbital, but if it's full, they'll just hang out in the 2s. But then again, Schrödinger also said, okay, so yeah, but we know that there's not 2 electrons at that second layer that can go up to 4, and so maybe that there are 3 orbitals extra, but they're not spheres, they're kind of dumbbell shaped, and we call those p orbitals. Schrödinger really predicts what's going on. That's really what we utilize today. The problem with it, though, is it's a bit of a pain to work with. The math starts getting much more difficult. Billiard ball model, there is no math. There's nothing to do. Bohr model, it's using some algebra. We don't usually do it in most of our classes because who cares? But you can definitely do it. Schrödinger model, all of a sudden you're now talking fairly advanced calculus to calculate what wavelengths of light are going to start interacting with the electrons and getting them to hop back and forth between various shells. Which is annoying. So if I could get by with no math in the billiard ball model, I will. And that's usually what we do. Because most of the time you don't really care about the light interacting with the particular photons. Or, sorry, the photons of light interacting with your nucleus. Now, we've got our nucleus. So, once again, this is tiny little speck, and you got the electron cloud around it. The nucleus is, once again, it's tiny, 1/100,000th the size of the atom. Basically, it's got all the mass of it, and it's got protons and neutrons in it. Neutrons, by the way, have no charge. Protons are positively charged, as mentioned earlier. Now, when we're looking at an atom, we want to understand what's going to go on with it. And when we're doing chemistry, the electrons are governing the chemistry. So how those electrons behave governs how the chemistry of the atom takes place. Well, what controls the electrons? The answer is the protons. So the protons are going to be determining how the electrons behave. Where exactly in space are those orbitals? How attracted are the electrons going to be to the nucleus? How easily are they going to be shared with or stolen by other atoms, etc.? Well, that means it's controlled by the protons, and the only thing you can do with protons is change the number of them. And so the only difference, the core fundamental difference between all of our atoms, all of the different elements, the types of atoms that we have, is simply the number of protons. They will have different numbers of neutrons. That's there really holding the nucleus together, because you get enough positive charge together, it's going to want to try and blow up. But really what's governing that element, what makes it, is the number of protons, and the number of protons is known as the atomic number. This is a counting number. You can't have half a proton. And so if we're going to go 1, 2, 3, 4, periodic table is basically arranged in order. 1, 2, 3, 4, 5, 6. It's got some turns, etc. But it's in order. They don't skip around because the patterns flow nicely with atomic number. Atomic mass number is taking the protons and the neutrons together. It's expressed in either atomic mass units or daltons, which are, shall we say, small. Now, once again, electron, very, very small, 0.0005 daltons, so we're talking tiny relative to that of a proton and a neutron, so we basically ignore it. Now, there's a couple interesting quirks. Turns out when protons and neutrons get together in a nucleus, their mass actually changes slightly. We'll talk about that in Unit 12 when we cover nuclear radiation, nuclear power, etc., which makes life interesting. Now, the reason we care about mass number is it has a couple of interesting features, but the major one that we care about is that we're going to track our atoms by weighing them. So we need to know how heavy our individual atoms are. Additionally, some atoms that have the same element but a slightly different mass, what we call isotopes, because they have a different number of neutrons, they're going to behave slightly differently. We can look at temperature by comparing water molecules that have an oxygen that has 8 neutrons versus an oxygen that has 10 neutrons. They're chemically identical, but it takes a little bit more energy to evaporate water made up of a 10 neutron oxygen, and therefore you tend to evaporate more of it when it's hotter and less of it when it's colder, so you can get an idea of temperature. But with that said, we're going to look at atomic mass number by protons plus neutrons equals our atomic mass number. Now, what I just alluded to, isotopes. Iso, same, tope, stuff. So these guys are going to have the same number of protons, same number of electrons, but a different number of neutrons compared to each other. Now, this is one of those relationship thing. You always have to have two. You can't just have an isotope. I mean, you could have an element that only has one isotope, but isotopes are talking in relative to each other. So you're talking one isotope versus the other when you're speaking about them. Chemically, absolutely identical. Some of them, the nucleuses don't hold together. Others they do. Ones that don't hold together are called unstoppable. We'll talk about that in Unit 12. Or not unstoppable, unstable isotopes. We'll talk about that in Unit 12. Ones that are stable, we call them stable isotopes, and we're just going to talk about them in generic, nothing too awful fancy. Now, it should be noted that when you have a block of carbon, you have a blend of isotopes. It's mostly carbon-12, which means 6 protons, 6 neutrons, a little bit of carbon-13, 6 protons, 7 neutrons, carbon-14, a tad bit of carbon-14, 6 protons, 8 neutrons, as well as a smidgen of carbon-11, which is 6 protons, 5 neutrons. And this is the same story goes for most elements. You've got to have a blend of isotopes. Chemically speaking, we're going to want to keep track of the number of atoms we've got of a type, not really of any particular isotope. So we're not going to use atomic mass number very much. Instead, we use atomic mass. So we're going to take the fractional abundance of each one. This is a weighted average. We're going to take the fractional abundance of each one of them, times it by its mass. So essentially, if we've got, say, 98% carbon-12, you're going to take 0.98 times 12, because that's the mass of your carbon-12 atom. And remember, that's the 6 and 6. And then if you've got, say, 1% carbon-13, that would be 0.01 times 13, and then you do the same thing for the 14 and the 11, which I have no idea what those are off the top of my head, and you add them up. Now, unlike normal averaging, where you divide by however many you had, you took care of that by doing the multiplying by the percent. This gives us average mass, and that one will be listed on a periodic table. Sometimes it's a blend, so depending on where on Earth you are, the blend of isotopes does change. That one we're going to use in Unit 6, and that's going to be important for counting atoms and counting molecules and counting the chemical, because that's actually going to be the way we start thinking about reactions taking place. Now, atoms can also have a charge onto them. So far, we've assumed that the number of electrons is equal to the number of protons. That's what we call an atom. But atoms can lose electrons or they can gain electrons. They can't gain or lose protons. If an atom has a different number of electrons than protons, then we call it an ion. A neutral atom, one where the number of electrons and protons are the same, each electron has a negative charge, each proton has a positive charge, and the amount of charge on them is the same. is just opposite. So they're going to cancel. So you have no net charge. If you lose electrons from an atom, it becomes what we call a cation, and it has a net positive charge. You don't have enough electrons to overcome the positive charge of the protons. If you, however, gain electrons, then there will be too many electrons, and they will not just cancel out the protons, they will go above and beyond that, and you'll have a net negative charge, what we call an anion. So the charge of an atom is going to be protons minus electrons is going to equal our net charge. And that once again be plus or minus. The confusing part, and the reason I made that quip earlier about too bad we had already defined the charge of protons and electrons, is that electrons are the ones that move. They're negatively charged. So we're going to say we add electrons, therefore the charge went down. It's a confusing statement, but it makes, it is true. The electrons are negative, so if you add a negative, the charge is going to go down and thus start becoming negative. But it is confusing. So that kind of starts wrapping things up. Next, we're going to jump a little bit further in, start thinking about what we're dealing with. But this is it for part 1.